luminance histograms are quite useful for showing you the apparent brightness of an image. But it's not very good at telling you when you're completely overexposing one particular color channel. So we've been talking about these unique color channels, this red, this green, and the blue, and the same sort of thing exists on a very physical sense in your digital camera. And of course, I have to hand wave and say we'll be talking more about this later, but you actually have this concept of red and green and blue channels in your digital camera, and it's possible that you can overexpose one of those channels. Maybe not the whole thing. So before, we've been talking about overexposure in terms of this pure white, where it becomes completely white and you lose all of the data in that white spot. But the same thing can happen to individual color channels as well. And for those of you that love to take photos of flowers, for example, you're particularly prone to this, particularly when you're taking photos of red flowers, for instance. If you oversaturate it, you will get an underexposed image, but there's so much red in there that it will actually blow out that color channel. You lose this information. So it's this complete red in the flower itself, but what you've lost is the detail within that flower. You just have this blob of color. And yeah, it looks really nice because it's this big blob of color, but there's no detail. You've lost the texture in that flower itself. So the luminance histogram is good for showing us apparent brightness, but it's not good for showing us when we've blown one of the individual color channels. That is what the RGB one is useful for. You'll notice that here we have this big spike in the upper end of the histogram. We can see that we're somehow overexposing this image, and that is with the red color channel itself. And to give you so I have to give you another ugly image, but bear with me for a moment. To give you an idea of this, let's say we have an image like this. So yes, this is abstract, but it's meant to show us a point. The point of this is that we have a lot of colors. We have red, green, and blue colors, but we don't have a lot of brightness change, really. There's no really white areas in this photo. There's no really very dark, very black areas in this area, or rather in this photo. So our luminance histogram reflects that. We see that there's 0 pixels in sort of this very bright upper region, and there's 0 pixels in this very dark lower region, but we can see that we have these spikes of blue, of red, of green, where we have, each of these individual sections of color. Now, keep in mind that your photograph will not look as blobular as this, and so you're not actually going to get very nice spikes with a luminosity histogram like 30% of the way in or 60% of the way in. It's more likely going to be a bit smoother, but this is just meant to show this one aspect of the histogram. Yes?
So if in the luminosity histogram, if blue is the color that there's the most of,
Yes.
that's the value that peaks, it'll just peak all the way to the top?
Yes.
All the other ones are relative to their proportion to that, so their peaks will be...
Right, that's correct. So if you have in a histogram a peak that goes to the very top of the graph, everything else is relative to that particular peak. So you could say that, okay, well, there's a lot of very red pixels, but it looks like there's only maybe like 80% of the number of blue pixels. And sure, green is brighter, that's why it's up to the right over here, but it's only like 30%. There's only 30% of really green pixels. And we can sort of see that in the image as well. There's less green than there is blue and red as well. So yes, it is a relative thing. The graph is always relative to itself everywhere else, if that makes sense. So even here, so this low point is relative to the very high point that exists. It doesn't sort of go off the chart, so to speak, but you can think of it that way if you want. Okay, but the RGB, what's nice about the RGB one here, and so this is an image that actually shows you the difference between what these histograms are measuring very, very well. Because here, the apparent brightness of the image, there's nothing that's, it's very, very dark. There's no very dark shadow region, and there's no very, very bright highlight region in this image. So that's why we get this particular luminosity histogram. However, we do have this very wide array of actual color information. So we go from some sections where, as you can see in this blue section, there's no red, there's no green, there's only pure blue. And then there's other sections that are that pure color, and there's pretty much everything in between, all these gradients between the red, the green, and the blue. And so we get this RGB histogram. So there's some areas where there's a complete absence of red, a complete absence of blue, complete absence of green, and combinations thereof. But there's also regions where we have the complete presence of each of these colors. However, we don't actually vary that much in terms of the actual brightness of the image. And so we can see, using the RGB histogram, regions where there's just no more detail. So we can imagine that if you remember going back to this sort of dynamic range that we were talking of. So we had this dynamic range and we had this tonal range. So we'd have a pretty good tonal range in this image because you can see kind of smooth gradients between each of these, these very, very bright regions of color. But because these gradients stop and all of a sudden it's just this pure color, you can see that the dynamic range of this quote-unquote scene is actually larger than that of what our image is capable of taking. So to make this become a little bit more concrete, imagine that we have something like this. So this is something that I alluded to earlier. If you take pictures of flowers, which can be very, very pretty, you can actually very quickly overexpose certain channels of color within that particular image. And I want to make this clear to you. So I'll try to zoom in. And if we look at the detail that exists within some of these flowers, you can see that, sure, you see the shape of the flower, and here you can see some of the detail, but in some of these very bright regions, you've lost the detail in that flower. So yes, it looks bright, and yes, in this case, it looks properly exposed, but we've actually lost some of the detail that's most important to this photograph, the actual flowers themselves. So this is something that you have to be watchful for. And this is a perfect example of how these different histograms can help us. So if we look at the luminosity histogram, it's just, we have sort of a big peak here in the left-ish end, and that's because for the most part, it's not a very super bright image. It's not like an image, if you imagine in your mind's eye, an image of pure snow, for example, which would be sort of glaringly bright. This is much more mellow than that, and it's reflected in the luminosity histogram. However, we don't see in the luminosity histogram the fact that we have blown out those particular colors in this image, that we have lost information in this image due to blowing out some of this color information. Yes?
So, I mean, because that exact same situation happened to me where it was very brilliant red flower, so brilliant yellow sunflower.
Mm-hmm.
How would you I mean, because the rest of the photos so how would you compensate for that without then going to the point of underexposure in other areas?
It's a complicated thing to try to solve. So if we're trying to solve this problem where we're still trying to keep the image as a whole properly exposed but not blowing out one of the color channels, I mean, we have a couple of options available to us. We could use that bracketing technique that I was talking about from earlier, where we take multiple exposures and then we find the exposure that as a whole it will be dark, but that has the most color information here. Then we can try to add it back into this properly exposed photograph. That will actually result in perhaps a slightly awkward looking photograph. It won't look very natural, in other words, just because we have this perception of what this photograph should look like, and if it suddenly looks very, very dim in very specific regions, if it has very, very low contrast in just very specific regions, we'll sort of detect that and maybe not explicitly, but we'll be able to think, oh, something looks off about this photograph. So another thing you could do is to try to lower the contrast or try to lower the saturation. And sometimes, if you were lucky, you might be able to recover some of the data back. Of course, the downside to that is that it just doesn't look as punchy. There's not as much color there. There's not as much of that good look. So there's not a lot of options there's no good option that we really have. Another thing you could try, I guess, would be to somehow alter the light in this scene so that, for example, let's see, you could try, let's see, you could try putting this section of flowers under a bit of shade, for example, and then because there will be less light there, you might be able to recover some of the details. But of course, it will be a little bit darker. It's a complicated problem, and unfortunately, there's no perfect solution. Pretty much anything that's going to recover that data is going to make it look a little bit darker, a little bit less contrasty, or some variation thereof. Or you could try, if you really wanted to go artistic, you could do that spot color technique, where people take they take only the color they want and then they make everything else black and white. It's a masking technique that we'll talk about masking later, but you could do something like that, which is cheating perhaps, but then when you only isolate that one color, then you could have all the gradations in it and the texture, and you're not changing its apparent saturation, if that makes sense. So it'll look saturated relative to that gray scene surrounding it, but it may not be as saturated as it would be in this particular case. So I'm doing a lot of talking, and basically I don't think there's a perfect option. It's just something that we have to try to combat using a variety of techniques. Yes?
I'm wondering if you were trying to fix this in the field rather than in post, would there be some type of filter that you could use to maybe keep out a little bit of the red while not affecting the green areas?
No, indeed, you could certainly use a color filter to try to filter out some of the color that exists in the scene. So if you didn't want to do, just to repeat for the camera, if you didn't want to do a lot of post-production, so you take this image into Photoshop and you don't want to manipulate it a lot there, then you could use a color filter, but there's a couple problems with that. First of all, you have to know color filters and you have to know which color filter to use, but then you will still have sort of the same effect where you were altering the amount of color in the scene, and it will change the apparent saturation of it. I think, let's see, so it will even change the relative saturation if you use like a, let's see, which one would it be? It might be a green filter to try to reduce the amount of red in it. Then you could, is that right? A cyan filter to reduce the amount of red in it. Then it would just, I think that would just make the flowers look very subdued in terms of their color, which sort of arguably destroys the point of the picture, which I think is the contrast in the color between the flowers and the green surrounding it. I guess another option you could use is a neutral density filter, but when I talked about neutral density filters before, I don't think I mentioned the graduated neutral density filters, which is basically, it's just like a gradient where it's completely transparent at one end and then it's completely dark, well, not completely, but some level of dark at the other end. And they have graduated filters for various colors as well. And you might be able to pull something like that off as well. Rather than actually putting it under shade, you could reduce the amount of light physically entering into your lens, especially down here, and then progressively have more light. So it's messy. It's not an easy problem to solve, in other words. So, okay. But coming back to the point of this, using the histograms, you can see that with luminosity, there's not a lot of indication that you've blown out that particular color channel. And I guarantee that when you're looking at this photo on your tiny digital camera screen, that's not going to be very apparent. What's going to be apparent is the contrast in the scene, that you've properly exposed it, and not the small little details that exist. So it's going to be something that's very easy to miss unless you look at these histograms. But if you take a look at the RGB one, you will actually be able to see, and it's difficult, but you can actually see a bit of a blip where you have actually overexposed a little bit of a particular color channel. And if you're lucky enough to have a camera that supports individual color channels, then you could actually see the red color channel individually, and you'll be able to see a very noticeable amount of clipping, as it's called. So there's too much information on this end, and so that's indicating to you that it's just too bright for the dynamic range of this particular camera. So it's easy to blow out colors, is basically what I'm trying to tell you. And using these histograms, you can try to figure out what has gone wrong and maybe be able to try to do something about it. So in the camera, you could just try to decrease the amount of exposure compensation. So if you go into negative exposure compensation, you could decrease the apparent brightness of that particular image. Okay. Now, when we are talking about histograms, we've been talking about the frequency of brightness, and especially as it relates to luminosity histograms within a particular image. And so one of the things that we haven't really talked about up until this point is how does a camera know what black and white are? So how does it know what values are black and what values are white? And we sort of alluded to this earlier when I said that there's this specific range that the camera is capable of capturing. Above that range, it's going to look completely white, and below that range, it's going to look completely dark. And so this camera may not have a concept of black and white, but just anything sort of beyond that range is going to automatically look to be black or white. And so that is what we're talking about when we're referring to this dynamic range. Now, if we actually had a look at this same scene, if we were each of us present at this particular scene, it would not look like this to us because our eyes actually have this very wide dynamic range within it. And so we have, thanks to our eye, a variety of things that happen. So so first of all, we have the iris, for example, which it's able to open and close dynamically and very, very quickly. So as we look across the scene, it can actually open and close to try to vary the amount of light that's entering into the eye. Our brain, in fact, will play tricks on us as well. There's a lot that's going on in the visual processing that is altering our perception of the brightness of the colors of the scene that actually exists in front of us. And our eyes can actually deceive us. And this makes it, though we're used to it, this actually makes photography somewhat difficult because our eyes are very, very dynamic. Our eyes would see this scene without so much of a problem. But unless you're somehow conscious of the actual range in brightness between this dark area and this light area, you're not going to know that your camera is not capable of the same dynamism. It's not capable of adjusting itself as much as we are. Well, it perhaps is, but just not on the same photograph. So one scene as we see it is not the same as one scene as a photograph sees it. So as you know that we have this, we can see varying levels of stops. And just to give you an idea, we are able to see the dynamic range of our eyes overall. So the amount of light that we're able to see in the darkest room versus the amount of light that we're able to see on the brightest day is about 1 billion to 1, or about 30 stops of change. And so that's, a billion times change in intensity is quite a bit. And the instantaneous dynamic range of the eye. So in other words, as we're actually looking at one particular object versus going outside and letting our eyes readjust, as we're looking at one particular subject, we actually have about 10,000 to 1 change or range in the brightness of something. So that's about 13 stops. That's in a bright day. When we're outside and it's bright and it's sunny, we can actually see about 13 stop change from the darkest areas to the lightest areas and still be able to perceive details. When we go into the dark, our range actually expands a bit. We get about 1 million to 1 dynamic range, or about 20 stops of change. So the dynamic range of our eyes changes based on how bright it is outside, a variety of factors. But what this should tell you is that we have a lot of stops of dynamic range, our eyes, instantaneously in one particular scene. And as you can guess, cameras don't have this same dynamic range. It's much more difficult for cameras. And so when we're talking about dynamic range of digital cameras, I like to use an analogy of a bucket. So imagine that we have millions of these little pixels or buckets within a digital camera. So as you know, we have 8 megapixels, 12 megapixels, however many megapixels your camera has that many million of these little pixel buckets. And these buckets collect light. And in this analogy, you can think of it as rainwater. So as rain falls onto these buckets, we're collecting the rain, and then after we're done, we measure the amount of rain in each of these buckets, and then that helps us figure out how much light there actually is. So as photons come in, it fills this bucket with collected light. And there's sort of a minimum amount. So as you can imagine, if you actually have a bucket that's outside and it rained a little bit, you go outside with the ruler and you try to measure it, and if it didn't rain enough, you're not going to get a very accurate measurement, right? You'll know that it's very small, but you just don't know how small it actually is. Maybe it was like 1/8 of an inch or 1/16 of an inch. Maybe your ruler just doesn't have that sort of resolution. The same sort of thing happens to us here in this bucket. And in fact, at the opposite end, let's imagine that it was like yesterday when it was snowing like crazy and we have a little tiny bucket, and all of a sudden this bucket overflows because there was just too much of this rain that fell. You can imagine that now we can't measure how much rain there actually was. There was too much for us to measure because it spilled over, and we know that it spilled over, but we just don't know by how much. And so this is the same sort of thing that happens in the camera. So we have a maximum amount of light that we can collect. We have a minimum amount of light that we can collect. And we can figure out what the dynamic range of our camera is just by using a very simple equation. We can figure out what the most amount is, so the quantity of a full bucket, and divide it by the quantity of the smallest bucket that we can measure, or the smallest detectable signal. So if there's too much rain, the bucket's overflowing, it's not readable. You know it's over full, but you don't know by how much. And in fact, if you'll let me take this analogy a little bit farther than I probably should, imagine you had all of these buckets that are right next to each other, they're very, very close, and you have one bucket that fills up very quickly and it spills over. It's going to also spill over into the neighboring buckets as well. So if you're really bad and you really overexpose a particular image, one of the things that can happen is this effect called blooming, where you have photons that almost literally spill over into the subsequent pixels, and it actually expands this region of overexposure to be a little bit brighter than it was in the scene. Yes? Yes, blooming also happened with film, but I don't know if it's the same sort of thing. I imagine that it's on a very high level, it's the same sort of idea, but that's much more of a chemical reaction versus an electrical change. And so the concept is very different, but a similar thing did happen, yes. Okay, so we have this equation then. We can figure out exactly how much, if we actually knew sort of the raw data of the sensor, we could figure out how much dynamic range our cameras have. And in fact, a lot of times, this same data is available to us. Just when we're looking at the spec sheet of a digital camera, we can figure out, without having to do any math, in fact, they just give us the data, how much dynamic range our camera actually has. And believe it or not, for modern SLRs, for modern digital SLRs, we can actually get between maybe 10, maybe 12 stops of dynamic range. And compact digital cameras, just by nature of the size of their sensors and a variety of other reasons that we'll talk about later, they actually have many fewer stops. Sometimes it's 5 to 6. Now they're creeping up. As technology matures, it's getting a little bit better. We might be up to maybe about 7 or 8 stops of dynamic range now in each of these cameras. And so you can imagine that this is one of the reasons that this is a bad thing for us, is that our eyes are capable of maybe a 13-stop change instantaneously, so we could have seen all these details that exist here, but the camera simply is not capable of recording that particular information. And so I have a question for you then. So why might digital SLRs have a little bit better dynamic range than compact cameras? Think of our rain bucket as an analogy. SLRs are typically bigger, Sensors might be bigger. So yeah, so we might have a bigger bucket. So we might be able to collect more rainwater then, so to speak, and we might be able to, we would then be able to collect more rainwater, so then we could have a better dynamic range. And that's just one of the reasons. There's a variety of other reasons as well, but that's certainly one of the things. And so with all of this in mind, I bid you farewell. So until next time, when we talk about more software tools, thank you for coming and bearing with me with the histogram, and have fun with your digital photos.